Hey guys, welcome back to the channel. Today we're going to be going over displacement, velocity, and acceleration versus time graphs. I'm going to be going over the things to note about each of these graphs, as well as a comprehensive problem to give you the strategy to apply to each question to ensure you get the right answer. By the end of this video, you'll be able to maneuver between all three graphs, as well as understand what the slope and the area under each curve represent. If you find this video helpful, please like this video and subscribe to the channel to see more videos just like this. Also, don't feel discouraged if you find this content difficult. Trust me, so did I when I was in high school, but the more problems you do, the easier it gets and the more your confidence grows. Stick around to the end of this video to learn the two most effective ways of studying. Okay, so before we go into each graph, I want to first go over all of the units for each of the vectors we're going to be using, which are displacement, acceleration, and velocity. So if you look here, and if you don't know this, I have a video going over the kinematic equations, and that'll be very helpful to understand kind of the units and why they're important. So here we have displacement, which is represented by d, and that has units of just meters. Next we have velocity, which is denoted by v, and that's in meters per second. And finally we have acceleration, which is a, and that's meters per second squared. So that's very important to note before we kind of look at all these graphs. But now let's look at a graph of constant slopes. So here I have a graph of displacement. I'm doing this in green, a displacement versus time graph. So if we had a constant slope, that would look like this. And if this was just a normal graph of like a y versus x, or f of x versus x, what we'd say is the slope is the rise over the run. So we'd say slope is rise over run. And in this situation, we can look at our rise and say, okay, well, what's our rise? Well, our rise, so rise over run, I'll say slope is equal to this. Our rise is d of t over our run, which is time. And then now, if we look at the units of d, well, this is meters, and in time, we have seconds. So now we can say that the slope of displacement versus time graph is equal to velocity, because velocity is in meters per second. And similarly, we're going to go scroll down to a v of t graph. So if this graph had a slope, we could do the exact same thing. So this is going to be rise, and this will be run. And here we could say slope is equal to rise over run. And our rise here, well, that's just v of t, so that's the velocity component, and then our run is just time. And in this situation, velocity is in meters per second, and then that's all over seconds. So if we write that a bit more clear, we can write slope is equal to meters over second times 1 over seconds, or divided by seconds. And that will give us a slope is equal to meters per second squared. And this are the units for acceleration. So now we know that the slope of a velocity graph is acceleration, and the slope of a displacement graph, and that's velocity. So now if we scroll down and go to something with zero slope, so if we go, this would have a constant displacement. This has zero slope because it's just a horizontal line. And if it has zero slope, here this object is not moving, right? Because if there's zero slope, and slope of a displacement versus time graph is velocity, that means that there's no velocity, there's zero velocity, so this is not moving. We have constant displacement, or I guess a constant distance away from where we started. Now if we look at a velocity graph, we have a constant velocity here. This will be constant v. Here we know that the slope of a velocity versus time graph is acceleration, but here we don't have a slope. The slope is zero. It's a horizontal line. Slope is zero. If we did rise over run, well, there's no rise, so that rise is actually zero, and therefore the slope is zero. So when the slope is zero, this means that there is no acceleration. So this particle or this object is moving, and it has a constant velocity, but it's neither accelerating or decelerating. So constant velocity. And finally, if we were to represent our acceleration as a constant, this would be a graph of constant acceleration. And here we could do the slope of acceleration, but it's not very common and it's not very useful. So there's not really a slope of this acceleration time graph that's useful. Okay, so now that we understand kind of the constant slopes, the zero slopes, now I want to go over to changing slopes. And this might get a little tricky, but if we apply the same principles in this kind of tip here, we'll always get the right answer. So here we have a displacement versus time graph. And I've marked kind of 2 points. So we have this, I guess, beginning point here in blue and this end point. If we look at this end point and beginning point and did the slope of that entire period, if we did like kind of the rise over run of this, right? Slope of blue is rise over run. What we're going to see is that's a positive slope, right? It went up in the positive direction in displacement and then over a positive time value. So this will be equal to positive. And if the slope of a displacement graph is positive, that means that the velocity is positive. But now, this has a changing slope. So we kind of looked at like the macro picture there, the, I guess, bird's eye view of this situation. But now I want you to look at these red points that I marked. And this is where the slope is actually changing. The slope over here, this red, if we did like rise over run here, it's very different from this point here. So right here what we have is the slope from, I guess, this first red point, so we could say beginning and then end. Well, this slope here would probably be somewhere around 0. It's almost a horizontal line. So, and then this slope over here, we could say that's 1 or 2 or just something bigger than the original slope. So it went from 0 to 1. That's also an increase or a positive increase. So we can say that this is a changing velocity, and the changing velocity is at an increasing rate or a positive rate. So that means that this object is accelerating, because the change in velocity, as we noted from this graph here, is actually, if we go here, the change in velocity, or the slope in velocity, is acceleration. So here we now have a particle that has a positive velocity and a positive acceleration, so it's speeding up in the positive direction. Next, we can go to a different changing slope graph, still displacement versus time. And again, I want you to look at the same situation. So here we have a beginning point in like the macro picture and an end point. If we look at that beginning and end point, we see that this slope is actually negative because it went down. The rise was actually negative. So we're going to have a velocity that is negative. And then I want you to look at the red points. So here we have a changing slope. The slope isn't constant throughout that process. So here we have a slope that is similar to 0 in like the last example. It's kind of like a horizontal line. The rise is very minimal for the run. And then we have a slope of, again, we'll call it just 1 to make things easy. Here, or sorry, negative 1, because it went down, right? The slope was actually in a negative direction. So here the acceleration is negative. So this object or particle is now has a negative velocity, and it's also speeding up in that direction. And we have 2 more cases of this displacement versus time graph. So again, it's going to be the same process. We're going to look at the beginning point and the end point and say, okay, is that positive or negative? And that will give us our velocity. So here, the rise was positive. So that means that the slope is positive and the velocity is therefore positive. Now we look at the acceleration here, or the change in slope. So here we have a slope that's probably equal to 1, and then the slope goes to approximately a horizontal line, so that could be 0. In this situation, the change in the slopes went from 1 to 0, so that's a decrease. So we can say now that acceleration is negative. And finally, and before I move on, when the velocity and accelerations are different, that means that the speed, and then when I say speed, I mean the magnitude of the velocity, so not the direction, is decreasing. So it's slow. The object is either slowing down in the positive direction or slowing down in the negative direction. Whereas in this situation, we had the velocity to be negative and the acceleration to be negative, so they matched. That means that now the object is accelerating and speeding up in the negative direction. And similarly with the positive direction, since they're both positive, that means that the object is going, or has a velocity that's positive and is also accelerating in that direction. And finally, we have the last case of this displacement versus time graph, where we have a beginning and we have an end. And here, the slope would be, well, this is starting at a more positive value, and this is actually going downwards, so it's going to be a negative slope. So slope is equal to, or I guess velocity, we could just write, is negative. And then looking at acceleration here, well, we have a slope that's probably -1, right? It's going downwards to start, but then it kind of flattens off. So we could say the slope here is equal to 0. And so -1 to 0, that's actually an increase. That's a positive change from -1 to 0. You'd have to like add 1 to get to that. So our acceleration is positive. So again, because this, or I guess I'll do it in green, because these do not match, what that means is the object is slowing down, or the magnitude of the velocity is decreasing. Okay, now that we've gone over slopes, I want to take a moment to go over areas. And after we have all this, we're going to have all the tools we need to take on a comprehensive problem and to take on most problems from here on out. So now, what I want to do is find the area. So here we have a velocity time graph. This is time, that's velocity of 20. And if I were to say, what's the area of this? I think most of you would say, okay, well, the area is just a rectangle. So it would be length times width. And you'd be correct. So we'd have area is equal to our length. So I guess in this case it would be our height, which is 20. And then multiplied by 10. So when we do that, we get an area of 200. But 200 what? What does that mean? So here is where we use the units and to help us out. So if we do the area, the first 20 value, that was meters over seconds. And then we multiplied meters over seconds by seconds. So here, these cancel out, and the area is just 200 meters. So the area under a curve of a velocity graph, area of velocity, is equal to the displacement. And this is always the case. So I want you to note that by doing the unit cancellation here, we now know that the area of a velocity versus time graph is displacement. Okay, next. Here we also have a velocity versus time graph, but it's now a changing velocity. It's not a constant velocity, so there's actually an acceleration component. But to find the area under the curve, we can still just use basic geometry and note that the area of a triangle is 1/2 base times height. Times height. The area is going to equal 1/2, well, our base is 10 and our height is 30. So if we do that, we're going to get 5 times 30 because 10 divided by 2 is 5. So the area will equal 150. And in this situation, we're still doing the same thing. We're doing our unit cancellation. So 30 is meters per second and 10 is seconds. If we multiply those together, we're just going to be left with meters. Okay, so that's the area under a velocity curve. So now we're going to go over to the area under an acceleration curve. So similar examples and similar shapes, but now we're going to go, okay, well the area under this acceleration curve, it's still going to be the area of a rectangle. So we're going to say the area is length times width. And in this case, it's going to be 5, I guess the 5 is the height or the length, times 10. So our area is going to be 50. But again, 50 what? So if we look at our length is in meters per second. And then or sorry, our length is in meters per second squared because it's acceleration. It's in the vertical axis here. So this is 5 meters per second squared. And then we're multiplying it by time, which is just seconds. So now these are going to cancel, and we're going to get area is equal to 50 meters per second. So, and noting that the meters per second, that's just the unit for velocity. So the area of an acceleration versus time graph is equal to velocity. So in this case, we had the area under a velocity time graph was displacement. Now we have the area under an acceleration versus time graph as velocity. And here we're going to do a similar example, and the area is going to be equal to 1/2 base times height, area of a triangle. And that is going to be area is equal to 1/2 10 times 10. So here we're going to get 100 divided by 2 is 50. Area is 50, and then here we have meters per second. Hopefully that all made sense, and those are all the tools that we need to now move on to a more comprehensive problem and tie all these kind of theories together. So moving into our comprehensive problem, and this problem is going to have kind of elements of everything we've learned so far in this video. So this comprehensive problem has a velocity versus time graph, which is graphed right here, and it asks, describe the motion of the particle. That's part A. Part B is draw an acceleration time graph, and part C is draw displacement versus time graph. So, before we kind of start this problem, what I'm going to do and what I recommend most of you do is, what we should do is section off each part of this velocity versus time graph. So I'm going to label this part here as 1, this part here is 2, and these are basically just sections. This is 3, 4, we have 5 here, 6, and 7. So now that we have we've broken up the problem, it makes it a lot easier to deal with. So the first problem of describe the motion of the particle. So let's look at section 1. So I'll write 1 here, and it's a velocity versus time graph, and there's a slope on it. So if there's a slope of a velocity versus time graph, that means that the object is accelerating. In this case, the slope is negative, so it means the object is decelerating. So we could say, I guess, particle is decelerating. 2, well, this line here, in section 2, the line is actually the same. The slope hasn't changed at all. The particle is decelerating. Okay. Now, what I do want to note between these parts is there's a yellow dot here, and that yellow dot is important. So what I'm going to say is that yellow dot, that passes through the velocity versus time axis, and what that means is, for a split second, the particle was at 0, or the velocity of the particle was 0, so it wasn't moving. So we could say stopped for this moment right here. Basically what's happening is it started at an initial velocity, it started decelerating, and then for a split second it actually stopped, and then started accelerating in the negative direction. Okay, so that's part 1 and 2. Now we have part 3, where we have a horizontal line. So a horizontal line, for whatever graph we're on, just means that it's constant. So we have constant, and what graph are we using? It's velocity versus time, so we have constant velocity. And it's actually in the negative direction, we could say, because it's kind of below the time axis. Next, we have section 4, and section 4 now has a slope, so we know that the object is either accelerating or decelerating because it's a velocity versus time graph. But in this case, the slope is positive because, this point at 15 seconds the point at 20 seconds is higher than the point at 15 seconds. So we could say particle is accelerating. 5, section 5. Okay, what happens at section 5? Well, this line, you can probably see it here. It's a horizontal velocity, so that means it's constant, but the velocity is actually on the time axis, so that means it's 0. So we could say particle is stopped. We have section 6, which is, again, another acceleration because it's a positive slope of a velocity graph, so particle is accelerating. And lastly, we have section 7. In section 7, another horizontal line on a velocity graph. That means that we have constant velocity. So that's part A. We've described the motion of the particle by breaking it up into specific chunks and describing each of those chunks. Now, what they asked us to do is draw the acceleration versus time graph. So acceleration versus time from a velocity graph is the slope, right? We said that if the velocity is constant, there's a horizontal line, then there's no slope of that velocity, so therefore there's no acceleration. But if there is a slope, there will be acceleration. So again, we're going to look at each of these sections and calculate the slope. So slope of 1 is going to equal, well, we have 0 as the final point and -5 as the initial point. So we have 0 minus 5 divided by, and then we have from, this is time equal to 0, from 0 to 5. So the slope, I should say, sorry, we should say 5 minus 0. So the slope is going to be -5 over 5, or -1. So that would be the slope for section 1. If we go to section 2, what we get is, well, this line is actually the same. So the only thing that's changed is the time interval, but the slope is constant because it's the same line from section 1. So the slope in section 2 is just -1. Now if we look at section 3, well, here there is no slope. And at that point we had constant velocity. So if there's something that has constant velocity, it's not accelerating. So we could say the slope is equal to 0. And now if we look at section 4, slope of 4, what's that going to be? Well, here we went from -5 to, so we went from -5 to 0. So our final thing was -5, but it's going to be minus -5 divided by, and then we had, what was that, 15 or 20 minus 15. So we're going to get +5 on top, +5 on the bottom. That means it's a slope of 1, which makes sense because it's an increasing slope. It's going in the positive direction. So it's accelerating in the positive direction. Now we have slope of section 5. If we look at section 5, well, here again it's another horizontal line. So we're actually not going to have a slope here. So slope is equal to 0. It's similar to 3. The slope of section 6, if we look at that, well, that went from 0 to +5, and then the time was from 25 to 30. So we're going to get 5 minus 0, and then 30 minus 25. Slope is again equal to 1. And lastly, we have the slope of section 7. Slope of section 7 is a constant velocity, so there's no acceleration. So again, it's 0. Slope is 0 of a horizontal line. And now we have our acceleration versus time graph to draw. So here we can look at all of our sections, how we broke it all up, and now just plot the acceleration versus time graph. So for section 1, there was a slope of -1. So if we go down here, we can write, we'll have this as -1 and this as +1. For section 1, I can write all the sections to make it very clear. 2, 3, 4, 5, 6, and 7. So for section 1, we had a negative slope. So it went like this. And then we had a slope of 2, which is also -1. So we kind of continued this over both intervals. Same slope. This should be as horizontal as possible. Let's see if I can. So that is the slope from sections 1 and 2 because the velocity had the exact same slope. And then we have slope 3. Well, that's 0. So what it's going to look like is this graph is going to be like this because the acceleration was 0, the slope was 0. So we have to mark that on this graph. Next, we had the slope of section 4, which is 1. So we can go up to 1 and then across for all of section 4. and then down. Section 5, there's no slope again, so it's just 0. Section 6, we have another slope of, let's see, of 1, and we go across. And section 7, we have a 0 slope, so it marks on the time axis. So this was part B, and this is why we drew why we calculated all these slopes, so then we could draw the acceleration versus time graph a lot more easily. Now moving on to section 3. So for section 3, we're trying to do the displacement versus time graph. And we know that the area under a velocity curve is displacement. So that's what we're going to be looking for using this curve, using this velocity curve. So again, I'm going to write out our sections. 1, 2, 3, 4, 5, 6, and 7. So those are our sections. And for each section, we're going to find this area here. I won't draw them for all of them, but we're looking for that. So in section 1, so I'm going to write for 1, the area is the area of a triangle. So it's base times height divided by 2. So we have the base, which is 5, the height, which is 5. So the area is going to be 2.5 times 5. 2.5 times 5 gets us 12.5 meters. Next, we can do the area of section 2. So the area for section 2, same formula, right? We have this triangle here that we're trying to find, like this. And for section 2, it's going to be 1/2 base times height, base times height. But here, the height is -5, so we have to account for that. So area is going to equal 1/2, so it's going to be the same exact area of section 1, but it's going to be -12.5 meters. Now we can move on to section 3, and section 3 is a little bit easier because it is the area of a rectangle. So now we can find this area, and that's going to be -5 multiplied by the interval, which is 5 seconds. So area is going to equal -25 meters. Now we're going to move on to section 4, and this is where you can kind of start using, I guess, symmetry or like geometry. 2 and 4 are the same exact triangle, it's just kind of flipped. They just now they're going to have the same area, but it's just going to be, well, it's still going to be negative because of the negative value of the velocity. So we're going to have area 4 is going to equal -12.5. 5 is going to be area equal to, well, the area here, there is no area because the line is exactly on the time axis, right? So the velocity was 0, so therefore the displacement will be 0. And then we have the area of 6. What do we have for that? Well, it's going to be base times height, and now the height is positive, so it's going to be 5 times 5 divided by 2, and we're going to get positive 12.5 meters. And finally for 7, the area is the area of a rectangle, so it's in here, and that's going to be 5 times 5, so 25 meters. Okay, so now we can plot the displacement versus time graph. We have all of the displacements in each interval. The only thing we need to note is that for displacement, it's going to look like a curve, right? Because we're plotting acceleration. We have acceleration in this kind of problem. And for all of those displacement graphs we went over beforehand, that has a changing slope, right? It was represented by those curves. So we know that the displacement graph, since it has acceleration, there's going to be some curves involved. But what we are going to do is we're going to look at the area for each section, and we're just going to put the point down. And we always have to think about the displacement and where it's traveled from. So in this first example, I'm going to do it in green. We're going to have 12.5, and then we're also going to have -12.5. We could have 25, I guess, and -25. So for this first example, for the section 1, and again I'll write down all these sections, 2, 3, 4, 5, 6, 37. So for section 1, the displacement was 12.5. So we're going to say that for section 1, we reached this point. We got to this point from our original, displacement of 0. So it's going to look something like this, some type of curve. For section 2, and again this is at 10 seconds, after section 2, it was negative 12.5. But we have to think about where we're first coming from. So now, our section 1 it's not going to be negative 12.5 down here. What it's going to be is it's going to be 12.5 minus 12.5. So it's going to come down like that. Now we look at section 3, and we see that it's negative 25. So negative 25 from 0, that's going to reach this point here. So again, we're going to have kind of a curve. It's not a good one. That looks like that. Then we have a negative 4, the section 4. It's actually going to keep going down, so I should draw that curve a little bit better. And I'm going to extend this line down. So if I draw this down here, $37.5. Now we're going to go to section 4, where section 4 is going to reach this point here. So we're going to have a curve that's going to go through this point and hit that point there. Now what happens in section 5? Section 5, there's no displacement. So we don't change our displacement from where we're originally at. So from section 5 to 6, the displacement just stays constant, and it just comes across to this point. So we're not adding or subtracting anything from our negative 37.5 displacement. Next, we're going to look at area 6, and that is 12.5. So if we go up to 12.5, that's where we're going to get. And finally, section 7, we're going to, so it's going to be negative 12.5 plus negative 37.5. So we're actually going to get to this value here, negative 25. And then from negative 25 plus 25, well, that is going to get us to 0. So back to the origin, or the axis here. And this would be part C. So this would be our displacement versus time graph. And so this one is a little bit more involved because we have to think about where the velocity is starting from and where the displacement is coming from, and we have to think about each interval as kind of their separate sections and then solve for the final answer. So, like I said, let's talk about the best and most effective ways to study and learn. These methods are always the active form of studying or learning. Passive forms include things like listening to a lecture, reading notes, whereas active forms are making those notes or trying problems. The first best active way to learn is by teaching others. And this is something that I've definitely experienced, and I think most have experienced. When you try to teach someone, you have to be able to communicate effectively, and you kind of have to convince yourself while you're doing it. So I really recommend trying to teach a parent, trying to teach a sibling, or just anyone around you, because when you try and recite it, it will be much harder to recite and communicate if you actually don't know the material well. So that's going to lead to higher retention rates, and it's going to be a more effective way to study. If you don't have anyone to teach, or they're not willing to learn from you, what you can do is just recite or teach a wall or a chair. What's going to happen, it might sound silly, but what's going to happen is you're going to realize that in order to kind of convince yourself or put the content in your own words, you're going to need to know the material very well, and your communication skills are going to need to be very precise. If you're unable to do this, you actually don't know the material well enough. The next most effective way to learn is to practice by doing or applying your knowledge. And this can be done by making notes. So that's taking textbook information or lecture information and consolidating it down into your own words. That's the value of making notes. Reading notes really doesn't lead to long-term retention rates, but if you condense material down, that's where you get a lot of the magic. And if you condense the notes down further, you even get more value, and it's going to be easier to understand the material because now you have less content to remember. Additionally is doing practice problems. So practice problems, especially in math and physics, are one of the best ways to study. They're super effective on having you actually understand the material by applying the knowledge you know and seeing if the concepts make sense in a problem or a real life situation. What I'd encourage you to do moving forward is, if you're reading notes or if you're learning the material from lectures or even these videos, try pausing the video and reciting back what I said or what you heard from someone else to see if you can make it make sense in your own words. Additionally, try pausing the video before the problem starts to see if you can get the right answer. Thank you for taking the time to watch this video. It's my goal to provide as much value as I can to everyone to help streamline the journey of a student. If you guys like this content, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. I make a ton of content to help in math and physics and to improve the confidence and psychology of students. If you're looking to get better grades and become more interested in the topics that you're learning, please consider subscribing to this channel. Thanks again for watching, and I'll see you guys in the next video.